Hello, this is Brian Fay, and this is INFOST 410X. Today we're going to answer some questions about data warehouses. For our first question, we have, what does it mean when a data warehouse is non-volatile? Well, to answer that question, we need to start with a little background on data warehouses. Data warehouses commonly store information for business intelligence and decision-making processes. Data warehouses tend to have an historical perspective. So what does it mean by being non-volatile? In essence, the data added to a warehouse never replaces the existing data that's present. New records can be added to the database, but that action never erases the old data. This aspect of non-volatility is one of the 4 key factors in database warehouse design, as stated by Bill Inman, the father of data warehouses. Now, one might ask why being non-volatile is essential in a data warehouse. Well, have you ever been contacted by a credit card company regarding potential fraud or suspicious activity in your charge account? The credit card company utilizes your purchase history to analyze patterns or behaviors to compare current purchases to determine whether or not they are possible fraud. If credit card companies simply deleted old purchase records when entering new purchase records, predicting fraud would be far more complex. We can see another example of why data warehouses need to be non-volatile in the storage of forecasts. Say we have a database that includes records for sales forecasts for the Acme widget company. Acme's sales department develops new sales forecast numbers each month and replaces the old records. When reviewing the company's performance, the company's new CEO asks the sales team how accurate the forecasts have been over time. Now, unfortunately, since the sales team deletes the old estimates, there's no way to evaluate the changes over time. Had the sales department used a non-volatile data warehouse to retain all monthly sales forecast numbers, they would have had the information needed to answer the CEO's questions. For question 2, we have, what is a fact table in a data warehouse? Data warehouse structures are commonly star or snowflake-based schema. And at the very center of that star snowflake is a fact table. Now, to better understand fact tables, we need to look at what's stored in them. These tables tend to hold measures, and these measures typically come from the day-to-day information stored in operational database systems. But a critical aspect of the data in the fact table is that it should be of equal grain or granularity. This means that the records in the table each comes from a consistent event, yielding a basic standard data set. Now, for instance, in manufacturing, that event might be each time a machine forms a particular widget. The moment the widget is created, the machine ID, the widget model, weight, and size, along with date and time, are all logged into the operational database. Fact table records would ultimately house the measures of weight and size, along with a combined foreign keys that link to the various dimensional tables at the points of the star snowflake schemas. These dimensional tables contain the date, time, machine ID, and model information that effectively categorizes the measures to ultimately support multi-dimensional analysis. For question 3, we have, when do you use OLAP? OLAP, or Online Analytical Procedure or Processing, is a database technology commonly utilized when querying data from a data warehouse as part of a business intelligence, data mining, or other decision-making system. The technology aids its users, such as business analysts and data scientists, by allowing them to aggregate data from multiple sources to answer questions like how fast a virus will spread, or to forecast automobile build trends. In contrast, OLTP, or online transactional processing, is a technology which deals with the day-to-day data transactions, including updates and deletions within production-level databases. OLAP streamlines analysis by focusing on read-only data access from large pools of data. Within the realm of OLAP, there are three common approaches: MOLAP, ROLAP, and HOLAP. The first, MOLAP, uses multi-dimensional storage and is fast, but is limited in size. The second approach, ROLAP, uses relational databases, making it a more scalable solution. However, as the dataset grows, the speed of queries suffers. Finally, the last method, HOLAP, attempts to combine the elements of the first two by using relational and multidimensional databases relative to whichever is more efficient for a given data set. For question 4, we have: what three types of actions do users typically perform when they use OLAP software? With OLAP, the three typical actions are slice and dice, drill down, and roll up. To better understand these actions, we first need to envision an OLAP cube. To do this, we start with numerical data referred to as measures. Then various dimensions categorize these measures into a cube structure. So let's say we have the measures that include automobile sales for each month of last year classified by make and model. The three axes of our OLAP cube are make, model, and months. Now, to perform the first OLAP action of slice, we choose one of our dimensions along the edge of the cube, and say, for example, we select a particular make of car, such as Ford. Using this selection, we effectively slice the cube to yield a subcube of sales numbers for all Ford models over each month of the year. Now, the dice operation takes this process just a step further. By selecting two or more dimensions, we could dice our cube by selecting, say, GM as the make and the first 3 months of the year as the period. Now, the following two actions, drill down and roll up, are similar but perform opposite functions on an OLAP cube. Now, if we look again at our cube of automobile sales and focus on the axis of time in months, we can see the sales for each week of each month if we drill down. Now, if we still focus on the month axis of our cube and we perform the roll up action, we can then see the sales for each make and model by quarter or by the year as a whole. Both procedures allow us to view the data at different levels of granularity. For question 5, we have: what is data mining? Data mining encompasses the examination of data stored in a data warehouse utilizing various techniques with the ultimate goal of observing patterns or trends that can support decision making. There are 6 standard classes of data mining. These 6 classes are classification, clustering, regression, summarization, associated learning, and anomaly detection. Now the first two, classification and clustering, are similar in that they both seek to group data. However, classification aims to fit data into known groups. For example, a bank might classify mortgage applicants by either being a higher or lower risk of loan default. On the other hand, clustering mainly focuses on categorizing information by similarities within the data itself, possibly identifying new groups. Now, the next method, regression analysis, is used more to tell us how likely something is to occur, possibly by how much or when. An example could be forecasting the price change of consumer goods, or estimating the number of hurricanes in a season. The next class, summarization, simply simplifies data sets like those used for visualizations. For associated learning, this is a method that is similar to clustering, but it also tries to relate the data to a particular event or location. Now, the final data mining process, anomaly detection, simply looks for data that doesn't match any given pattern. Question 6 was a little different. The goal here was to listen to the story from Radiolab regarding a real-life data warehouse. Then to research what Amazon.com is using now for its data warehouse solutions, and to research and find examples of other data warehouse technologies being used. Now for the Radiolab story, it is effectively about a real-world version of a data warehouse that uses people and actual warehouse goods instead of computer-generated data. In the story, the orders were effectively the queries, and the people or runners acted on those queries to gather physical products, and that was the actual query result. Now for true data warehouses, Amazon has been marketing since 2012 its Redshift cloud-based data warehouse solution. The name Redshift implies a shift from Oracle, one of the most well-known database system providers. Amazon Redshift platform is a software as a service or platform as a service that allows subscribers to support business intelligence and data analysis functions using up to a mind-boggling petabyte level of data capacity. In addition, it uses massively parallel processing, which yields rapid responses to queries. And although Redshift is an OLAP-style column-oriented database, it also handles standard SQL queries. Some of Redshift's customers include well-known businesses such as Fiserv, Yelp, NASDAQ, and McDonald's. In addition to Amazon's Redshift, 2 other well-known cloud-based data warehouses are Google's BigQuery and Snowflake. BigQuery is a serverless solution that also supports analysis up to petabyte levels of data with SQL queries. Customers of Big Data, or BigQuery that is, include Twitter, UPS, and Home Depot. Snowflake, a software as a service, launched in 2014 and runs on Amazon S3, Microsoft Azure, and Google Cloud. Customers of Snowflake include DoorDash, Kraft Heinz, Instacart, and Pepsi. The interesting comparison between BigQuery and Snowflake is that while Snowflake utilizes OLAP, BigQuery by Google states that its ad hoc queries actually eliminate the need for traditional OLAP tools. This is Brian Fay, and I want to thank you for joining me in going through these questions about data warehouses.